All right, welcome back everybody. Before we start with the course material, I have a couple things that I want to discuss just to bring everything to closure in many cases. First thing I want to say is with regard to the term exam and all the marking and changes and the like, this is the final grade distribution. I did go through and make the change to allow things like acid instead of acidic, base instead of basic to be correct answers. I can't go through and correct for spelling errors, so if you spelt it wrong, there's nothing, it's just impossible to put in all the possible variations. So I did make the obvious changes, and this is the ending resulting grade distribution. You can look on this grade distribution and kind of see where you sit in relation to the rest of the class. With the average in the around 68%, which is actually kind of where I was hoping it would be in the 65 to 70 range, things look good. There's a nice distribution of grades. We're done the unit on equilibria and problem set 4. I mentioned to you that your quiz is going to be this week. It will open up on Thursday and close on Saturday. So Thursday, Friday, and Saturday will be the problem set quizzes. A number of students have, I'm not going to say concern, but they've pointed out or voiced frustration with all of the math that is in Chem 101. And that is actually by design. Chem 100 is primarily a conceptual course. Lots of talk about theories, fundamental units and calculations, but it's mostly conceptual about bonding and the like, with a little bit of math in terms of the gas laws. Chem 101 is very mathematical. Equilibria, thermodynamics, electrochemistry, very mathematical with a little bit of conceptual material, such as the molecular interactions component that what we're going to be starting in just a few minutes. It's by design to do this, and some students find the conceptual stuff pretty easy, some students find it hard, some students find the math easy, some students find the math more challenging, just to realize that there is a difference in how the content of Chem 100 versus Chem 101. On that note, we do have some larger objectives beyond teaching you the course material, and this is something that I talked about at the beginning of the term, but I wanted to bring it up here. This looks at the level of the learner, yourself, where students generally start university as passive or active learners, and the goal of moving through the undergraduate program is to move them up to being active and engaged learners for an undergraduate degree, and then self-directed if they choose to continue on into graduate programs. It's not comfortable for learners to be pushed into doing things that they find inherently challenging, but it is required and an expectation of your future employers. So my job is to challenge you. We're pushing you into applying and analyzing data. We're not getting you to evaluate other work or create new concepts at this stage, but that is something that you will be expected to do as you progress through second, third, and fourth year undergraduate. The instructional strategy, I'm guessing you're really comfortable with the instructor-led instructional strategies. You're not that comfortable with guided or learner-led, but problem solving, having me do a problem in class, and then saying, hey, here's a similar one for you to do, is uncomfortable, but it does push students to learn the course material. Bloom's analysis of instructional strategies looks at this. So at the bottom end of this, lectures, videos, demonstrations. That's all instructor-led instruction. Instructor-led problem solving, questioning, think, pair, share is an instructional strategy. Here's some ideas that instructors engage students with. Okay, still low-level Bloom's analysis, low-level on Bloom's taxonomy. Then moving to the next level, student-led problem solving, simulations, that type of idea, where we are engaging students to take more responsibility. And at the top of it, the laboratory activities. Now, if you were working in a lab, then you would have a much little more frightful, I guess would be a term, working with chemicals and the like. We don't have that, unfortunately, due to the pandemic, but that is a high-level activity. We can compensate for that to some extent with the individual projects that you are doing. Your research projects or your investigative projects, using the correct terminology, are high-level Bloom's projects meant to challenge you. You are expected to independently investigate and report on some aspect of chemistry in the real world. It is expected to be challenging. Some people are going to jump at that and run with it. Others a little bit concerned because they're not really sure what to do. Again, kind of by design. With regards to that, chemistry is not just H2O plus, I don't know, NaCl going to form salt water. It's not just things that can be written down. The realm of chemistry can be divided into three groups. One of them would be synthetic, taking chemicals, mixing them together, getting products out. That's synthetic chemistry, whether it's organic or inorganic, you're making new compounds. Another realm of chemistry is the quantitation or the analysis. Physical chemistry, analytical chemistry can be applied in environmental, med lab sciences. That's your equilibria, thermodynamics, electrochemistry, all different types of quantitation in chemistry. And the third one is biological. Biological chemistry is the analysis of living organisms from a chemistry perspective. We don't have the ability to write chemical formulas, C2H6 plus O2 goes to whatever, from a biological perspective, but you can do cartoony style things. Here's an antibody, here's an antigen, they connect together and it triggers T cells to come, and I don't know the biochemistry, so forgive me on that. That is all realms of chemistry: synthetic, quantitation, and biological. And your research program can encompass sit in any one of those realms. With regards to that, your project outlines for your presentations are due Thursday evening. Emailing them to your TAs. So the TAs that you engage with for the lab that you've been assigned to are the TAs that you would email your project outlines to. There was one more slide on here, and again goes back to the idea of how much do you remember. Passive instruction is on the low level. Active instruction, engaging students in activities in the classroom and outside the classroom, has a much larger retention. And so I strive to do Q&A, question and answer in the classroom, put people out in breakout rooms and have them work together. I'm fully cognizant that the breakout rooms are not ideal because I can't figure out which breakout room having difficulty. In a classroom, I would do the exact same thing, work with the people around you, and then someone would put up their hand and like, we're lost, we don't know what to do. Well, then I could come help you. But in the current environment, it's a little bit more challenging, but that puts the onus on you to, take up that challenge, honestly. And I think that's it in terms of the stuff that I want to discuss before starting the course material. Does anyone have any questions on that? And Jada, I did answer your question. Yes, they are due Thursday night. All right. So to continue with the next module is molecular interactions, and it is chapters 12 and 14 out of Perducci. I'm going to half apologize, but also I'll be on time. You have what was made available to you yesterday was the lecture notes for chapter 12. I'm still finalizing the lecture notes for chapter 14 and the problem set, but they will be forthcoming. That is out the next day or so. So expect them to be, the finished material to be available to you by end of day tomorrow. With regards to Chapter 12, Intermolecular Forces, looking at liquids and solids, we're going to be looking at the first 4 units of Chapter 12. And to begin, we are, up to this point in time, spent a lot of time looking at intramolecular bonding. Intramolecular bonding is what occurs between atoms to form molecular compounds. Carbon-carbon bonds, carbon-oxygen bonds, oxygen-hydrogen, oxygen-sulfur bonds. Those are all intramolecular bonds. And the typical bond energies for intramolecular bonding is between 200 and 900 kilojoules per mole. The focus of this chapter is on intermolecular bonding, sometimes called van der Waals interactions. And this is bonding between molecular entities. So one compound here, another compound there, and they interact. They interact because of the electron clouds, the charge distributions in the different entities. We see this interaction because intermolecular bonding is responsible for the formation of solids and liquids. Okay, 2 free-floating atoms, molecules, come together, they condense to form a liquid, and then they can solidify, crystallize to form a solid. Intermolecular bonding is responsible for all of the macroscopic properties of matter that you see. Melting point, boiling point, density, viscosity. Anything property that you can measure of matter is a result of intermolecular bonding. Those bond energies are between 0.1 and 50 kilojoules per mole for molecular compounds, and between 60 and 16,000 kilojoules per mole for ionic compounds. And we're really going to kind of break this up to talk about intermolecular bonding in molecular compounds first, and then ionic compounds after that. But yeah. We have 3 distinct types of charge distributions. Induced dipoles are transient partial charge distributions. Dipoles are permanent partial charge distributions, and ions are permanent integer charge distributions. And we're going to look at all 3 of them in this chapter. Just to touch on ions before we put it aside, we've dealt with ionic bonding for a lot. Metal and a nonmetal, positively charged metal, negatively charged nonmetal, electrostatic interaction that forms sodium chloride, calcium oxide, whatever it happens to be. Yes. So that's ionic bonding, and we've seen that quite a bit. What we are looking at now is dipoles. And when you have a difference in electronegativity between atoms, and you looked at electronegativity in Chem 100, when there's a difference in electronegativity between the atoms, you have a polar bond. And the thing we're interested in here is called the dipole moment. The dipole moment is the sum of those polar bonds. And we're going to see through example that in some cases, while there might be a polar bond in that direction and a polar bond in the other direction, that symmetry ends up canceling it out, and so you have no net dipole moment. So let's think about what happens at the moment a golf club impacts a golf ball. Golf ball is small and hard, yet when you hit it with a golf club, you see a significant distortion of the golf ball. But very quickly after that, that golf ball reforms its shape, this one's actually elongated a little bit, it's overextended itself, and in the next frame would be back to its uniform spherical surface. This is exactly how induced dipoles are formed. So when you have either an atom or a molecule that doesn't have a dipole moment, it's complete. You have the centers of positive charge and the centers of negative charge are in the same location. So if we look at the top atom on the right-hand side, that top atom has 10 protons in the nucleus and 10 electrons that are uniformly distributed around the nucleus. So the center of positive charge and the center of negative charge are in the exact same location. That, by definition, is no dipole moment. But what happens when this atom or molecule impacts something? So in the impacting with the wall, as presented on the right, the electron cloud distorts. And in this case, the electron cloud concentrates closer to the wall. Now the center of positive charge and the center of negative charge are in different locations. So with the center of positive charge and negative charge being in different locations, you have a temporary or transient dipole moment called an induced dipole. Now, if the electron cloud is on one side, all of a sudden, to anthropomorphize, they realize that there's a lot of electrons there, so now they distribute to the other side. And then they are eventually oscillate, resonates, and eventually that electron cloud comes back to being more and more uniform. The transient or the induced dipole gets smaller and smaller with every resonation, and you end up getting back to your original symmetric shape that doesn't have a dipole moment. There is no transient dipole moment in the final picture on the bottom. Now this picture, 10 protons, 10 electrons, as an atom, that's neon. Neon is a small, hard, compact atom that is very much like a golf ball. It will distort, but it very quickly reforms its symmetric spherical shell. Bigger atoms take longer, more oscillations back and forth to get back to being uniform and symmetric. We can induce dipoles through any number of processes. When you absorb heat or light, causes electrons to move around, and you get an induced dipole. Intermolecular collisions, or collisions with the container wall, as presented on the right-hand side, it causes the electron cloud to distort. Being close to a polarized entity. If you have something that has a charge, an ion or something with a dipole moment, just by being close to it will draw the electrons over or it will repel the electrons away, and so you'll give you an induced dipole. And the same thing happens with electric or magnetic fields, causes the electron clouds to resonate and distort, causing induced dipoles. This is a simple example, but it's an example I'm going to come back to a few times today. If you think back to when you were a child in a bathtub or having to bathe children or nieces, nephews, or someone, one of the things that kids in a bathtub like to do is cause the water to cause waves. And so they move themselves back and forward, and they cause the water to slosh up and around. That child is the external energy source, and the water is your electron cloud. And the electron cloud up there, over there, up here and splashing out onto the floor, that type of idea. That is the distortion of the electron cloud caused by the child moving in the middle. As soon as the child stops, that water goes up, but it's less and less and less and less every time, till eventually you get a uniform, flat surface as it goes back to its normal, uniform distribution. As an example, we want to draw the carbon dioxide molecule, and look at bending vibration with regards to dipoles and induced dipoles. So carbon dioxide is this molecule right there. It is linear. And of course the oxygen is more electronegative than the carbon. So both of those bonds are polar. Those bonds are polar. The electrons preferentially move towards the oxygen because it's more electronegative. But because they are in equal and opposite directions, we have no net dipole moment. When we look at a bending vibration, now I'm just going to go back over to here. This isn't an analytical chemistry course, but I do want to tell you that the atoms aren't just sitting there. And so let's call my head the carbon atom, for lack of a better example. My hands are the oxygen. It's not just sitting there doing absolutely nothing. There is motion of the atoms around in every molecule. And there's what's called stretches, where they move out in and out uniformly or opposite, whatever, and bends, where you actually are bending the bond. I'm not going to go into a lot of detail on any of those. I just wanted to point out that there's a lot of things that you will see in future classes, but right now I'm only really interested in the bending vibration associated with CO2, which involves the oxygen atoms moving in an, I'll just do it this way, the oxygen atoms are moving in an up and down direction. Like that. So in one instance, it looks like this, where they're, oops, wrong color. At this point in the bend, there is a net dipole moment going downwards. At the next point in the bend, again, there is a net dipole moment now going in the other direction. So with the bending, you see a transient dipole moment produced. Or an induced dipole moment. How do you cause a molecule to stretch or bend? You absorb heat. If you move, when we take analytical or analytical chemistry, what did I say? Organic or analytical chemistry, we will see that when you absorb infrared radiation, you're causing vibrations and bending within molecules. So that's the absorption of that heat. Polarizability is the ease in which the electron cloud in a molecular entity are distorted. So going back to that bathtub analogy, water is really polarizable. It's weak, it's light, those things, the water moves everywhere, and it moves everywhere quite easily, and it takes a long time for it to level out. However, if that was oil in the bathtub or molasses, okay, viscous fluids, it's a lot harder to cause that electron cloud to distort, and it's faster for it to return to its normal uniform distribution. That's polarizability. Okay, the polarizability of the electrons determines how big of a transient dipole, how big of an induced dipole you're going to produce. The polarizability increases with increasing atomic number Z. I mentioned neon is small, 10 electrons, 10 protons, and hard. It's not very polarizable. But xenon, another noble gas, much bigger, The electrons in xenon are further away, and they're much more polarizable, and so higher polarizability for xenon in comparison with neon. Bonding electrons are more polarizable than non-bonding electrons. So while xenon has the 10 electrons around that single nucleus, methane, CH4, has the same number of electrons. It's the same mass approximately, yet 8 of those electrons are now in chemical bonds between carbon, the carbon and each of the hydrogen atoms. So there's 8 bonding electrons, and we're going to see that those bonding electrons are much more polarizable. The way we can measure polarizability is by looking at the boiling point, and we're going to see that in just a few minutes. The boiling point of methane is much higher than that of neon because the bonding electrons are more polarizable. Before that, we're going to look at this, which is the number of different entities, and identify whether they have induced dipoles, dipoles, or ionic charge distributions. So we want to identify the entities that have induced, dipole, or ionic charge distributions. Before we start with the individual molecules, I just want to point out that everything has induced. Even if it has a dipole moment and an ionic component, that electron cloud still distorts. And so everything will have induced dipole interactions above dipole and ionic if those dipole and ionic interactions actually are present. But we want to look at the entities, and I'm going to draw them on the right-hand side and then put them into the correct category. By drawing them, hopefully this will remind you of their structures and the processes from Chem 101. Ozone has this structure right here. It is a bent structure as presented here. But because all of the atoms are the same, there is no bond dipole and no dipole moment. So ozone only has induced dipole interactions. Wrong one. Calcium carbonate. Okay, I really don't need to draw the structure of this because you should realize that calcium is 2 plus and carbonate ion is 2 minus. So this fits as an ionic entity. Next one is So2. Sulfur dioxide is a trigonal planar parent geometry, but one of them is a lone pair, and since oxygen is more electronegative, it is permanently bent, and so there is a net dipole moment that goes down through there. So SO2 has a dipole moment. Oops. SO3 puts another oxygen atom there. This is a trigonal planar geometry, and it is symmetric. So each of these bond dipoles actually cancel themselves out, and there is no net dipole moment for SO3. How about CS2? What's the structure of CS2? If you look on the periodic table has sulfur directly underneath oxygen. So the structure for CS2 is actually the same as it is for CO2. It is linear with bond dipoles in equal and opposite directions that cancel each other out. So CS2 does not have a net dipole moment. SF4. Do you remember SF4 from Chem 100? What was the structure or the geometry of SF4? Anyone remember? It's not square planar. It's also not tetrahedral. What other geometry can you have with AB4? Square planar was one, tetrahedral was another, there's one more. What is the geometry associated with trigonal bipyramidal? Because this starts off trigonal bipyramidal. Except one of them is a lone pair of electrons. That's trigonal bipyramidal, yes, but when one of them is a lone pair of electrons, what do you have? Anyone? Octahedral is 6. Back to childhood. What's on the playground in childhood? That's the one. It's a seesaw geometry. Good. It's a seesaw geometry. And fluorine is more electronegative than sulfur. And because it isn't symmetric, well, hold on. The ones going in opposite directions cancel each other out, but the ones going down do not, and so there is a net dipole moment going in the downward direction. The end result is that SF4 has a dipole moment. Na2O. Well, it should be fairly obvious. This is ionic. Just assigning oxidation states because you can. So this is there. Similarly, CuBr2, copper bromide, is also ionic, -1 + 2. C2H6. When you draw ethane, you end up drawing it in many different ways, but two things come out of it. One, the bonds are in general paired with something on the other side. So there is a degree of symmetry associated with this, and ethane, is generally considered not to have a dipole moment. Wrong one. C2H6. The other thing is that most organic chemists will say that the difference in electronegativity between carbon and hydrogen is pretty small. It's about 0.2, 0.3, and that's negligible in comparison, so the bonds are really not that polar either. So carbon-hydrogen bonds are not considered to be polar by organic chemists. Physical chemists, myself, would say that there is a small bond dipole, but it becomes pretty hard to measure in large organic molecules. The next one is NaN3. And NaN3 looks really like some ionic compound, and it is. As a matter of fact, it's called sodium azide. And it's an explosive. I'll get to your question in a second, Mark. Sodium azide is an explosive. As a matter of fact, it's probably the one explosive that everyone I am talking to has been within about 2 feet of. Where do you find it? Not in well, yes, you can find it in pyrotechnics too, but it's an explosive that you've been in close contact with. Not fireworks. Don't think everyone's been within 2 feet of fireworks. Guaranteed 2 feet. And to some extent, you're relieved when it goes off. Your phone. Only when we want to get rid of you. No, not your phone, Cassidy. Nice try, though. Not combustion in the car, but you're getting closer. It only goes boom once. The airbag, right. Sodium azide is the active ingredient chemical in airbags. And so its detonation is what is used to inflate the airbags. So there we go. Mark's question from above. If it was an alkene or an alkyne, can you say it was a dipole? No. So in terms of alkenes and alkynes, as a matter of fact, the alkene is perfectly symmetric. That one doesn't have a dipole moment guaranteed because everything completely cancels because of the rigidity of the double bond, and the alkyne, similarly, is a perfectly symmetrical molecule and no dipole moment there. Good question, Mark. Excellent. The last one is hydrogen peroxide, H2O2. Structure of hydrogen peroxide, that should be an oxygen. The hydrogens are never in the same orientation. They're never exactly opposite. That's actually a high energy state for hydrogen peroxide. So there's always going to be bond dipoles and a net dipole moment. So H2O2 has a dipole moment. Good questions and good speculation there on your on the responses. So, all right. So with regards to intermolecular bonding, the bond strength ultimately depends on the type of charge distribution, as one would expect. Induced bond strength increases with increasing polarizability. Dipole strength increases with the dipole moment. And ionic strength increases with ion charge. When you have entities that only have induced dipoles, you only need to consider the polarizability. For entities that have dipoles, you need to consider the polarizability and the dipole moment because it plays a part as well. For ionic entities, you need to consider the polarizability, the dipole moment, and the ion charge in order to determine the overall total bond strength. And with those three types of charge distributions, we have several possible types of intermolecular bonds. If you have two things that only have induced dipoles, it would be an induced dipole interaction, sometimes called London forces, although I don't use that term that often, but your textbook does. If you have dipole interaction, ion-ion interaction, or the mixed interactions, dipole with an induced dipole would be, for example, oxygen dissolved in water. Oxygen is induced dipole, water is dipole or hydrogen bond, and so that would be the interaction of oxygen, dissolved oxygen with water is a dipole-induced dipole interaction. If you have salt water, sodium chloride in water, it would be an ion-induced dipole interaction. Each ion is surrounded by water molecules, that's ion-induced dipole interaction. Sorry, that's wrong. That's ion-dipole interaction. Water is a dipole. Salt are ions. Ion-dipole interaction. I was just reading the other one. My apologies. Salt water, the ions in water, ion-dipole interaction. And we're going to use the boiling point as an indicator or a measure of bond strength. We're going to start by looking at single component interactions, induced dipole, dipole-dipole, and ionic bonding. And as I mentioned, induced dipole is sometimes called London forces. So to start, induced dipole interactions is the weakest intermolecular interaction. Typical energies are between 0.1 and 10 kilojoules per mole, and of course it increases with increasing polarizability. And below that are some examples. Start off with helium has 2 electrons surrounding the nucleus. Hydrogen has 2 electrons, but those are now bonding electrons between the 2 hydrogen nuclei. The boiling point of H2 is much higher than that of helium. It's 5 times higher. Because instead of being tightly bound to a single nucleus, it is now in a bonding region between 2 nuclei, causing the bond strength to go up. Neon and fluorine, you see similar interactions there. You just go down the group. Neon has, when you condense to form the liquids, neon has more polarizable than helium. Argon, krypton, and xenon, increasing polarizability, increasing boiling point. Similarly, F2, Cl2, Br2, I2, to the point that for bromine and iodine, the polarizability is so strong, the interaction is so strong, that bromine is actually a liquid at room temperature and iodine is a solid. If we go over to the far right-hand side, there's a couple more examples. I'm just going to do the one on the bottom, neon and methane. Neon has a boiling point of 27, 10 electrons all around a single nucleus. Methane has 8 bonding electrons. The boiling point is now about 4 times higher due to the fact that those bonding electrons are more polarizable. But in general, the induced dipole interaction is generally very weak. So under ambient conditions, 25 degrees Celsius, 300 Kelvin, these entities are typically gases. To look at things with dipole-dipole bonds, occurs between entities that are polar. The typical energies are between 1 and 25 kilojoules per mole. And now when we look at the example on the top left-hand corner, we already looked at neon and methane, induced dipole only, no dipole moment. HF, same number of electrons, about the same mass, but it now has a dipole moment. And 1.83 d Debye, that's actually a fairly large dipole moment, but the magnitude, the actual number is not relevant, just the fact that there is a dipole moment, which means the boiling point is quite high, 293 Kelvin. Similarly for the one below that, argon, CO2, and HCl, CO2 has 8 bonding electrons, and here we're seeing the polarizability of those electrons being equivalent to, or about the same as that in HCl. Even though HCl has a dipole moment, there's only 2 electrons that are part of that bonding side of it, so HCl and CO2 have a similar boiling points. Over on the right-hand side, nitrogen, oxygen, both things that have no dipole moment. As soon as you form NO, that small difference in electronegativity gives it a small dipole moment, and the boiling point is slightly higher. When you put more bonding electrons, more difference in electronegativities to form CO bonds and the like, you get a larger dipole moment, and the boiling point is considerably higher. So, and the comment at the bottom, some induced dipole bonds have comparable energy to dipole-dipole bonds. CO2 versus HCl. Xenon and HI are comparable. Okay. Now, we did have a little chat about hydrocarbons earlier, where we were looking at ethane and then ethene and ethine. When we get to larger and larger entities, we can still look at it from the perspective of the CH bond is relatively nonpolar. The more compact we make the molecule, the less polarizable it is. So pentane, everything here is C5H12. The linear pentane molecule, those electrons have a larger ability to resonate, to move. When you put 2-methylbutane or 2,2-dimethylpropane, you're making a smaller, more compact entity. The electron cloud is harder to distort, so the boiling point ends up going down. One strong form of dipole-dipole interaction is that between hydrogen and an electronegative element, nitrogen, oxygen, or fluorine in general. Okay, that forms a hydrogen bond. You need to have the hydrogen bonded to nitrogen, oxygen, or fluorine, and that interacting with other nitrogen, oxygen, or fluorine atoms in the system. It forms a strong dipole-dipole bond with energies between 10 and 40 kilojoules per mole. So in the table, anything with a star forms hydrogen bonds. So neon and methane do not, but NH3 forms hydrogen bonds, so does water and HF. Excuse me. And interestingly, water is even above both ammonia and HF, and we're going to look at that in just a few seconds. Similarly, going down the list of HF, HCl, HBr, HI, HF is unique for many different things. It was a weak acid. We looked at that the other day. But it has an anomalously high boiling point because it engages with hydrogen bonding, which doesn't exist for HCl, HBr, and HI. And on the last example, argon, HCl, methanol. Methanol engages in hydrogen bonding. All of those are about the same mass. So here is where we can see this in a pictorial representation. Water, HF, and ammonia all do not follow the same trend in terms of boiling points. Carbon does. It continues to decrease, going from period 2 to 3 to 4. The reason why water has a higher boiling point, it goes up much more than ammonia and HF, is because the properties of water are such that you have the ability to form the perfect number of hydrogen bonds. Ammonia, with more donors than acceptors, can still only form one hydrogen bond. Similarly, HF, with 3 acceptors and 1 donor, can only form one hydrogen bond. Water has 2 donors and 2 acceptors, and so it can actually form 4 hydrogen bonds. And I'm just going to finish with this next slide. So here is the hydrogen bonding when you produce ice, and every water molecule is fixed in position in ice due to the fact that the 2 hydrogens on water bond with 2 lone pairs of electrons on other water molecules, oxygen atoms and water molecules, and the central oxygen atom has 2 lone pairs of electrons that it can engage in hydrogen bonding with adjacent water molecules. So this gives a strong structure, which means that its melting point and boiling point are anomalously high. And that's where we're going to end it for today. So if you have any questions, just feel free to ask them. And otherwise, have a great day, and we'll chat with you on Wednesday. Thank you.